Okay, I think we might make a start, and we might have a few more people trickling in as we go. If anyone's having any troubles hearing me or Eva or seeing the presentation, just give me a little chat in the chat box down in the left-hand corner, and I'll see if I can sort that out. So welcome to the Earth Systems and Climate Change Hub Science Webinar Series. Today's presentation will be given by Dr. Eva Cougnon from the Institute of Marine and Antarctic Studies in Tasmania. And Eva's research is part of the Hub's project on access decadal predicting systems. And today she'll be talking about towards predicting ocean temperature extremes. So without further ado, I'll pass you over to Eva.
Thanks, Sonia. So yeah, first of all, thank you for the opportunity to talk today. Is it working? So yeah, okay, it's working. Sorry. So today I will be talking about some work. Some of the work we've been doing under NESP, the Earth System and Climate Change Hub. And we are based, so as Sonia mentioned, at the Institute of Marine and Antarctic Studies at the University of Tasmania in Hobart. And we're also working with people based at CSIRO and also at Dalhousie University in Canada at Halifax. And so today the work I will be introducing is looking at ocean temperature extremes and the predictability of these extremes, or the potential predictability of these extremes. Just briefly, that's the overview of my talk. We'll give some background on why do we care about surface ocean temperature extremes and what are they. And also give a little bit of background on the ocean dynamics around Australia, like the ocean circulation around Australia. And some example about temperature extremes. And then I will finish, the last part of the talk will be on potential predictability in a way to define region of focus, where we're most likely to understand a bit better what can drive these extremes. All right, so first of all, why do we care about ocean temperature extremes? So here are a few examples about the impact that extreme in ocean temperature can have. So I will tell you now, like that I'm probably biased because I'm sitting in Tasmania, but like most of my examples are based in example in Tasmania, but most of them are also applicable anywhere else. So an example of impact on fisheries and aquaculture, that's Pacific oyster farms. In Tasmania in 2015-16, we started to have what we call the Pacific oyster mortality syndrome. That is quite bad for oyster farms. So like the picture here, it's a dead shell of one farm, one season after the POM syndrome was active. So yeah, like, there is a need to understand a bit better how this syndrome is linked to temperature and how we can manage it. Another example for impacts, it's on wild abalone. And we know that we get a higher mortality in the abalone community during warm events. Two examples were in 2011 on the west coast of Australia. In 2011, it was strong event, warming event, and there was pretty high mortality rate in the abalone. And also of Tasmania in 2015-16, so that was another warming event for Tasmania, where there was also an increase in mortality in abalone, not as strong as in Western Australia, but significant enough to notice. Another example in aquaculture is Atlantic salmon farm. So warm temperature for the salmon will can reduce the performance of the salmon and then limit the supply to the seafood market. So that's what happened in 2015-16 in Tasmania. I will come back to this event. I'm realizing that I'm talking a lot about this 2015-16 event, but I will describe it a bit later. It's just that's the most recent big event for Tasmania, so that's why I'm using it. So ocean temperature extreme do not have impact only on fisheries and aquaculture, but it's also all the ecosystem or the marine habitat that can be impacted. So that's an example of the giant kelp on the east coast of Tasmania. I can't remember exactly where in March, so about a year ago, like the kelp looked all right, and in December, well, it disappeared. So that's picture taken in the same spot. And what happened is like the water got relatively warm, I think around October, November, and which is probably the cause of that. But the thing is, it's not only the kelp that disappears, it's all the organism around. So for instance, if we look at those red patches here, they're actually red and growing because they need to grow under the shade of kelp. When the kelp is not here, there will be too much light for them to really survive. And you can imagine that all the environment, all the fish who live like in this environment will be impacted by that as well. And looking at changes in ecosystem and distribution of species, there was this study that didn't look only at marine species. They also looked at terrestrial species, and just so not looking also only on short warm events, but more looking along the trend. It seems that species are the distribution of species is changing and moving forward, but following the global trend of climate change. While extreme climatic events, like such ocean temperature extreme in the ocean, like a very warm event, will be also a key driver of this biodiversity pattern. And the frequency and the intensity of those events can actually have major implications on species distribution and ecosystem structure. Just to put Australia in a more global context, there are two regions in Australia, Southeast Australia and Western Australia, that are considered as global marine hotspots. So there are two regions that are considered to be major marine region around the globe to be experiencing very rapid changes in sea surface temperature. So like in these studies, they just looked at sea surface temperature from different products and identified a region where it was where the trend was stronger. So Australia, ocean temperature extreme around Australia have also like a big place for the whole globe. A bit of background on the ocean circulation around Australia. To understand those warm events in the ocean around the coast, well, we need to understand a bit some basics on the circulation. And the ocean circulation is actually quite interesting around Australia because it's quite a complex network of currents. Because we have two main type of currents. We have interbasin connection, which goes through the Indonesian seas, north of Australia. And we also have in the Southern Ocean, the Antarctic circumpolar current flowing eastward. And we also have boundary currents along the coast, the east and west coast of Australia. We have the East Australian current and the Lewin current along the west coast. They're both flowing forward and carrying warm water. So I'm going to spend a bit of time on those boundary currents because they are quite interesting in themselves. So like those currents are directly linked by the circulation in subtropical gyres. So what we call subtropical gyres is like, for example, in the South Pacific, we have this huge circulation, this huge gyre for the South Pacific that spin anti-clockwise. And then the west branch of this gyre corresponds to the East Australian current. And this region is what we call eddy-rich region. So like if we look at the plot on the right, so we have the East Australian current flowing southward, then turning back eastward. But we actually have what we call the extension of the East Australian current, which is part of the East Australian current going southward and having like those like what we call eddies spinning and going south. And this is a relatively warm current. On the west coast of Australia, so it's called the Lewin current, and this current is quite unique because for an east, so we call that eastern boundary current because it's on the east of the basins we're looking at, so east of the Indian Ocean. And this current is actually flowing poleward instead of equatorward. All the other east boundary currents around the world flow equatorward. And it's like a region to compare with will be, for instance, the coast of Chile, Peru. It's on the east side of the Pacific Ocean. And this coast is associated with high primary productivity. And there we're going to have like fish-based fisheries, while the Lewin current, and it's mainly because it's flowing the other way around, we have low nutrients there, and so we have a totally different habitat, and more like a seaweed habitat and sailfish kind of industry being able to develop there. So it's quite unique compared to the rest of the world also for that. But coming back to ocean temperature extremes, so what are they pretty much? So they could be like warm or cold events as well. However, cold events, they are less documented, but we do know that a cold thermal stress on certain marine species can have also a negative impact as well as a warm thermal stress. And warm ocean temperature events also expected to increase in intensity and frequency in the future, mainly because of the warming trend that we get in our data. So that's, this schematic at the bottom illustrates that quite well. So like on the left half of the plot, we just have like the temperature varying between warm and cold, so we get both cold and extreme events. While when we add a warming trend, well, we having more often of the warmer temperature. And if we look at this plot in a different way, so if we look at it in terms of probability of occurrence, so what I mean by that, it's just a distribution of the time series. So like just with this parabolic shape at the top of the parabol, basically that's the value of the mean. So on the x-axis, we have the temperature. We have the probability of occurrence on the y-axis. And then where we have the highest probability, it's, in this case, it corresponds to the average temperature. And then on we go down on both sides where it's less likely to get those temperatures, and that's where we found what we can call the cold tail of the distribution and the warm tail of the distribution. In a warming scenario, so we will shift this average a bit closer to the warm, and then we're gonna get like more of the orange that we had in the previous distribution, and even warmer. So just like another way to see this shift, but I will reuse this type of diagram a little bit later. All right, a way to identify region where extremes can be quite important. It's to look at the variability in the time series. So if I come back to this plot, for instance, we can look at how the mean of the time series is changing month after month, for instance, or year after year. And here I'm looking at the sea surface temperature anomaly and how the mean changes. I think it's going a bit slow because I don't know if you have the same screen, but I have like two plots at the same time. You should see only the top one. What we see where like the regions are darker on these plots, it shows that we have a higher variability in the sea surface temperature anomaly, and that's where we will find the extremes. If I'm looking at the variability of thresholds that we could use for cold extreme, let's say, so that's basically like this dashed line and how it changes over time, and we can do that the same for the warming. So like I'm actually looking at what we call the 19th percentile, so that's will be like 10% of the value observed along the time series will be above this threshold, and same for the cold, 10% below the threshold will be like considered cold extremes. And we can find similar patterns of where the variability is. So we don't see very much difference just looking at those three plots. But when I do the difference of the warm threshold and the cold threshold on the left, I can get this difference map at the bottom. And what this map tells me, it's like the variability of the warm extremes in the boundary currents that I described earlier along the west coast of Australia and southeast Australia. The warm extreme has a higher variability than the cold extreme. So meaning that warm temperature will, like it's more likely to have a warmer extreme in those regions. And this kind of way to look at the data was previously used in 2014 with model. So they did pretty much the same thing on the variability of the sea surface temperature, where on the left, that's controlled simulation, so like what pretty much like a model up to from the 90s compared to a projection in the future with a warming scenario, and where this variability is. And like we can see where we have the increase in variability, and so that's also a sign of where we're gonna find the warmer extremes. So some example of ocean temperature extremes around Australia. So as I previously mentioned, in 2011 along the west coast of Australia, there was a very strong warming event that they've never seen before. Like the peak of the period lasts for about 2 weeks with sea surface temperature 5 degrees above normal. Which had significant impact on coral and fish. They also had a reduction in the abundance of seaweed habitat and shift in fish community as well. So they observed species that they used to see a bit further north. And this event was directly associated with La Nina climate variability, so El Nino, La Nina climate variability. I will come back to that in a second. And from there, people started to use more and more the term marine heat wave that you probably heard of. So like from not only from this event in 2011, probably a bit earlier, but that's only after this warm event then people started to use a definition for it. And I took actually this plot from a website of an international working group who's working on marine heat wave specifically. And in this international working group, there are quite a few Australian-based scientists involved in it. And basically what they came up to, it's to be called a marine heat wave, it needs to be above a certain threshold that varies seasonally. So we can define marine heat waves in summer, but also in winter. So just comparing with a winter mean, sort of. And this, to be called also marine heat waves, needs to last for at least 5 days. And in Tasmania and southeast of Australia, actually, we had, it was like the longest and most intense marine heat wave ever recorded for this summer. It lasted for over 200 days and almost reached 3 degrees above climatology. So it wasn't as intense as in WA, but it was longer. And same again, it had like impact on the ecosystem, and with new disease outbreak, for example, the POMS that I introduced earlier, the Pacific oyster mortality syndrome, was first seen in Tasmania during this summer. And we also saw species that were coming from further north that we're not used to see along the coast of Tasmania. And the driver for that was associated with the dynamic of the East Australian current, and like especially the importance of the extensions that was bringing warm eddies south. And also in this study, they also did attribution, what we call an attribution study. So it just like basically they compare that, like they wanted to know how much of it was due to climate change and how much is just natural variability, the natural changes in variability. And they estimate that at least 6.8 times this event was almost 7 times more likely due to human, like anthropogenic climate change. Just briefly about 2 other events in 2016. Northern Australia and the north of the Pacific had 2 of their 2 big events as well. So in Northern Australia, it was this drove bleaching of coral of the Great Barrier Reef, and in the Bering Sea, Gulf of Alaska, North Pacific, it was quite interesting because it looked like the warming of the ocean fed back onto the atmosphere, and that led to modified rainfall and temperature patterns for North America, so US and Canada. And same, these 2 events were several times more likely due to human influences on the climate. Right, so like from that, well, what like under our project, what we want is to so there is this need to better understand the ocean temperature extreme and their driver to better predict those extremes. And so if we can predict them and understand them better, we can adapt, or we can like start thinking about how to adapt. And I've been using mainly observation-based products, satellite products of sea surface temperature. And I'm also using some model simulation in collaboration with component 1 of our project, led by Terry O'Kane, is at CSIRO in Hobart, who's looking at decadal prediction system. This work is pretty much under progress, so I'm not going to talk much more about it, but just wanted to highlight that we're trying to work with them on that. And the idea is like to get some predictability information in a form that can be used by other people. So I did first like to know what can drive the variability of ocean temperature. I just did a basic comparison with, and so that's a time series of El Niño Southern Oscillation, ENSO. And I compared this time series with a time series of sea surface temperature for a point east of PNG, so in the western equatorial Pacific, where it's directly the temperature variability there that is known to be directly related with El Niño Southern Oscillation. And what I did is I looked at the time series of this temperature during El Niño years and during La Niña years. And what we can see, again, on this probability of occurrence histogram, so black, that's the entire time series, red, that's only using El Niño year, and we can see like the shift of the distribution towards warmer temperature. While during La Niña, it's towards colder temperature. So that's great. That's an easy way to see what can drive the variability. I did the same for a point west of Australia, so along the west coast of Australia. As we know, like the event in 2011 was driven by La Niña, and like we can see that in this type of plot as well. Like the blue was during La Niña year, it brings the temperature in the warmer side of it. Looking at a point east of Tasmania, well, it's a bit more complicated. We can't really tell anything just by looking at those plots. So we need like some more complex analysis. So for that, I'm using what we call a potential predictability method. And well, the idea behind this method is to identify where the interannual variability is a useful fraction of the total variance. Like, that's something that we could predict given that we have a perfect model. So to give a bit more information, the concept is to decompose the time series into a slow varying component and a fast varying component. So the slow varying component will be part of the time series that is that varies with a longer time scale than a year, while the fast will be everything that varies with a time scale less than a year, season, for instance. And then we can look at the variability of those components, the variance of it, like the figure I've shown at the start with like the three orange panels, kind of the same idea. And then we can do a ratio of those variance of the slow varying component over the total signal. And this, like, when it gets closer to 1, so this ratio would be between 0 and 1. And closer to 1 means that it's driven by the slow varying component. So like it's driven by something that has a time scale of a year or more. While if it's close to 0, means that that's a fast varying component that explains most of the signal. So like things happening at a shorter time than a year will be driving will explain most of the signal of the ratio. So doing that, I can get a map like that where we can highlight regions of higher potential predictability. And we find again the same regions along the west coast of Australia, the western equatorial Pacific, the Coral Sea area, and around Tasmania, New Zealand region. And what I want to do from that, because what we get here, it's only information that in those regions, what drives the signal, it's something that has a time scale of more than a year, but it doesn't tell you what is this thing. So I want to decompose this variance in things like maps that I can understand. So I want like to be able like to have like plots like that where I can have like, for instance, like the plot on the left, it's the patterns that explain 30% of the total variance of what's happening in my data. So another way to see like the way I decompose those data, here it's just a little schematic to just understand a bit better the method. It's like we have spatial and temporal data, and like we have variability through those each of those snapshots, both spatial and temporal. And basically, we want to reorganize those. Reorganize those data into individual clusters in space and time. So, like that, it can give us pattern and time series that we can understand. So, yes, like we can like just looking at the variance of everything, we can get different pattern, different modes. So using that, it's like, for instance, like this one, the first pattern explains 30% of the total variance, while the second pattern will explain like 18% of the total variance. And we can see like this very red patch, which means that this mode, this pattern explain the variability mainly around this region. And for the third one, like we can now understand the variability that is happening in this region, southeast of Australia. So we kind of like divide like where the variability is, and then we can understand a bit better. Because for each of those patterns, we can also have a time series associated with that. And then from the time series, as I showed before, we can then compare like a time series of a smaller pattern. We can compare that to a climate mode again. So that's what I did here. So on the x-axis, it's different months, but let's focus just on the time 0 for now. And on the y-axis, it's the correlation coefficient. So basically what I did is like I took the time series associated with this pattern, and I compared it with the time series of ENSO, the El Niño Southern Oscillation time series. And what we can see, it's like when I compare them, I get a correlation coefficient of -0.5, which is quite high. I also get a significant coefficient correlation when I compare the time series with a time series of what we call the Ningaloo Niño index. So that's basically the variability, climate variability along the west coast of Australia. Then if I go along what I call like my month leads, for instance, in if I take 10, well, if I would have had strong number associated with 10, it would have meant that whatever climate mode that was high for this time, it would mean that that this climate mode would drive or will give information 10 months in advance on the sea surface temperature anomaly variability that we compare to the pattern. But here we can see that we can compare only at time 0. So when we compare directly the time series of the pattern with the time series of the climate mode. Looking at the second pattern, so where we had a stronger signal along the west coast of Australia, well, we get at time 0. So when I compare the time series with the time series of the Ningaloo Niño, so we have a strong correlation, which makes sense because the Ningaloo Niño index is based on what's happening in this region, more or less. And if I look at these blue curves that correspond to the ENSO index, I can see that 5-6 months lead, so like at 5-6 months in advance, ENSO may give some information to the sea surface temperature anomaly variability. So we might be able like to find information depending on the variability of ENSO at 5 or 6 months in advance to the sea surface temperature. For the last mode that was more southeast Australia, So if you remember the histogram I've shown earlier with 1 point east of Australia, we couldn't really see any clear relationship between ENSO and the variability in this region. When I compare the time series of this pattern with any of different climate modes that I've tried, well, it's quite complex as well. There is none that none of them are really clear. But if I look at 5 months in advance, it looks like ENSO may give some information to our data, which means that ENSO may actually have, in some extent, may drive the variability of the sea surface temperature. So having those information, that's where we want to use model simulations. That's where they're going to be useful in a way that we know where we want to look. We know a bit better what we want to look at in those model simulations. And basically what we want to know is to evaluate the skill of predictability of those model simulations by characterizing a time series of, characterize the time scale of the predictability in the model for predictability in extreme events. And if possible, identify a precursor sign to, again, characterize the time scale of the predictability corresponding to those specific regions. All right, so that's about it. Here, just a brief summary to highlight again the importance of Australia and marine extremes around Australia, just being a global marine hotspot, as they call it. And those events are really important to understand in the way that they have a strong impact to our fisheries, not only fisheries and aquaculture, but also the social economic system can be impacted in some extent. And now, with these potential predictability studies, we know a bit more where we want to focus looking at model simulations. All right, that's about it. So thank you, and happy to get any question.
Okay, well, thank you very much, Eva. That was excellent. We do have a couple of questions, primarily from Nathan. So I might just read through the questions and comments and get Eva to respond. So the first question is from Nathan around, what is the evidence for POMS, P-O-M-S, and heat waves? Is it really temperature dependent? Was it a fluke in 2015-16?
So I'm not quite sure if it's temperature dependent. At least, I guess he means why POMS arrived in Tasmania, right? Because I don't think we know really why it is.
Maybe I won't. Yeah.
And I have weird echo.
So really, is POMS a disease, or is it a temperature-dependent stress? That's the question I was asking.
100% sure. Yes, I can answer this question. I will probably send you to a contact, Sarah Ugaldi, who works at IMAS, who's a specialist for that. My understanding, though, is that it is sort of a disease, or it's because it appeared we already had those temperature before 2015, but it appeared since this event 2015-16. And same even for Australia, this POMS was first observed in New South Wales in 2010 and wasn't really observed before. But yeah, I'm not really an expert in that to really say more.
All right, I'll just keep reading through. Nathan makes a comment then, the greater occurrence of the warming extremes is where the trend has also been included or removed. you know if you wanted to comment on that, Eva.
So yes, there are two different ways to look at the data. Of course, with the trend, we're getting more and more of warm if we keep the same threshold. So just if I can come back or not. So yeah, like what we want also to know is like if we remove the trend, do we still get those extremes? Because oops, do you still hear me? Because everything is frozen on my screen.
Oh, we can hear you fine. Yes.
Okay, good.
Did you want me to click on
frozen? So yeah, we have like the warming that will bring, if we look at only one threshold in temperature, we will have more of this threshold. But if we remove this trend, and that's what I'm doing, like we're really interested of, well, even without the warming, do we still get like those extremes? And yeah, we do. And when I mentioned earlier that extreme events are predict to occur a bit more often, like to increase in frequency, it's without the global warming trend that we have.
Mm-hmm. All right, and then Nathan makes a comment that an interesting fact about the 2015-16 heat wave is that it also occurred with dry spring, costing millions and emptying of dams for power generation, and also a record wet autumn, and has also been attributed to human influences, so not just ocean consequences.
Yeah.
Do you want to? Okay.
No, not really. Yeah, no, I don't have anything to add on that.
Actually, I was really making a point that it's not just the oceans that showed strange behaviour in 2015-16. It actually influenced what happens on the terrestrial environment. And while that story hasn't been fully connected up, Tasmania had hundreds of millions of dollars of damage from the dry and the wet spell over the terrestrial. So the oceans are actually an important communicator of information, actually, for where we live. Just a minor point I'd like to push on to you guys.
Yeah, that's a really good point. Because my focus on the ocean, but yeah, it's not only all about the ocean.
Mm-hmm. And then we have one last one from Nathan. Does the lag of 5 months for the Southeast Australian with MEI make sense?
Haven't dig that. Yeah, so MEI, that you know that's MC index. But yeah, no, I'm not quite sure what to answer there.
Did you want to say anything, Nathan, or are you good on that?
I was looking for the physical meaning of, so is it the propagation or the circulation pathway between, I don't know, the Coral Sea and the spin-up of the EAC and the build-up of the... So that's where I was going. It's the physical connection rather than just the statistical relationship.
Yeah, I've been looking mainly at statistical analysis. I haven't been doing much work on really like what triggers it. I'm expecting like to do that a bit more with the models where I can actually look at changes in subsurface temperature, etc. So just like to trace it back to where it could come from and hopefully link those for instance, 5 months lag things.
Mm-hmm. All right, and then our final question comes from Pep Canadell. He asks, is there a statistical significant increase of sea surface temperature anomalies in the historical record for Australia? And how long is the historical record?
there is an increase in SST with historical records. So, like, for instance, a figure I've shown from a paper, like when I was talking about the global marine hotspots, paper by Alistair O'Day and Greta Baker, I think in 2014, if I remember well, one of the first slides. So I can't really go back on my slide, sorry.
Do you want me to go?
If you can, yeah.
What number slide?
That's a good question. I would be just after the impacts. Anyway, so like they looked at the trends in the trend of the sea surface temperature, and that's where they identified those global marine hotspots. And they were using, so for historical data set, so there is a satellite record that goes back to 1982. There is also the data set from the Hadley Center. It's called HADISST1. And so they based on like different sort of information plus satellite records since 1982, and they go back to 1871. So it's quite a fair way back. So yeah, that was the historical record, and I think in the paper I was mentioning before, they probably using another set as well. That I will refer you to. Yes, I will refer you to check the data set they used. Hope that helped.
Okay, well that's all the questions that we have. If anyone wants any more questions, just quickly type it in that chat box. Otherwise, I'd like to thank Eva for her presentation and for being part of the Earth Systems and Climate Change Hub webinar series. Just a little plug that next month on the 17th of April, we're having Nathan Bindoff present on an update on the IPCC special report on the oceans and cryosphere in a changing climate. So stay tuned for that. And thank you everyone for attending. Thank you.
Thank you.